Hello and welcome to the first event of the Festival of Disruptive Thinking, brought to you by King's Entrepreneurship Institute. My name's Tom Hunter. I'm going to be your moderator for this event, AI and the Digital Biology Revolution. It's my absolute pleasure to welcome you all today. I hope you're going to enjoy this. For those of you not familiar with the Entrepreneurship Institute at King's, they believe that everyone could be entrepreneurial, and that entrepreneurial people can help make the world a better place by solving problems to create a healthier, smarter, more equal and sustainable future. If you'd like to find out more about them, I will be putting some links into the chat as we go. And you are also all very welcome to use that chat function to put in questions for our presenter, Jorge. As we go, we will have plenty of time for a Q&A session at the end of this. This is all about disruptive thinking, but also disruptive conversation. And so for us, we want to make sure to spend plenty of time, not just to present ideas, but also to be able to discuss them. So do feel free to put your questions into the chat at any time, and then we'll come to those at the end. A quick bit of housekeeping as always, please do keep your microphones switched off along with your video. That would be hugely appreciated. And with that all in place, let me introduce you to Jorge Cardoso. Jorge is a reader in artificial medical intelligence at King's College London, where he leads a research portfolio on big data analytics, quantitative radiology and value-based healthcare. He's also the CTO of the new London Medical Imaging and AI Centre for Value-Based Healthcare. He has more than 12 years of expertise in advanced image analysis of big data and artificial intelligence, and co-leads the development of Project Monai, a deep learning platform for artificial intelligence in medical imaging. I haven't quite finished yet. He's also a founder of BrainMiner and Elytra, two medical startups aiming to improve neurological care and breast cancer diagnosis, respectively. I probably pronounced one of those slightly wrong, Jorge, for which my huge apologies. But because the floor is now yours, you're not only welcome to correct me as we go, but also thank you so much for your time today. Really looking forward to your talk, AI and the Digital Biology Revolution. Jorge, the floor is yours. Thank you.
Tom. I hope the sound is okay. So sorry, I think you lost me for a second. Can you hear me?
You're back now, Jorge. This is a great start to we're being disrupted.
Happening with
let's try that again.
With a disrupted. I hope it works out. Yeah.
I'll let you know, Jorge.
What I was trying to get to, yeah, I'm going to just take you a bit on the journey of what's happening at King's College London when it comes to using data to transform the way that we're providing healthcare to patients across the UK. And a little bit also about my research and larger pieces of research happening currently in the UK, supported by large infrastructure. So before I go there, one part that I would like to focus on is on the use of AI in healthcare. So as you know, in healthcare, there is a lot of data being collected for all purposes that you might imagine. And that data is being used to care for patients. So we normally take that data, clinicians use that data to understand what the patient might or might not have, to be able to diagnose and prognose what's going to happen to these patients. And normally that data stays there inside of an hospital, pretty much in use until you require and you need to go to the hospital again. But there's a lot more that data could help with, right? The data most of the time just sits there, and it represents an immense value. It contains a lot of information about what worked, what didn't work, what worked for you and what didn't work for you, but also what would have worked at the population level, how hospitals work with each other and how patients interact with the clinical systems. So we should be making more of that data. We should be exploring that data at scale. And in order to do so, we need to be able to create infrastructure, and we need to be able to create platforms to make use of that data and to transform it and make sense of it. And then after that data is all transformed, we can then make use of that data to inform care provision, improve the way we care for patients, and etc. So when we think about artificial intelligence applied to healthcare, we think about somehow this magical black box that is able to diagnose patients in a perfect way or being able to decide what are the treatments that we should give to different patients and things like this. And in that setup, we normally think about improving patient care as the primary objective of using AI in healthcare. So we tend to think about predictive systems, these intelligent systems. And by doing so, we will be able to diagnose everyone. And if we can diagnose everyone, then that's it. We solve all our problems. And there is a part of AI in healthcare which should be and it will be very focused around patient care. But actually, the use of AI in healthcare is much broader than this. When you provide a service to a patient, when you care for a patient, there's many things that happen through that pathway. For example, you need to make sure that the patient is correctly diagnosed and prognosed upon, obviously. You also need to make sure that the clinicians have the information that they need at the right time. So this is what, for example, I call here clinical efficiency. So AI algorithms can be made to choose what is the right information that is needed to care for a patient, to summarize information that wouldn't have been summarized otherwise, to be able to transform, for example, complex information such as the medical imaging data into measurements of the sizes of tumors or the types of tumors they're seeing, and etc. So there's a huge amount of efficiency that can be gained by extracting information from data and presenting it to clinicians at the time that they need it so that they can make their own clinical decisions. Then there is the systems of auditing. So when you are receiving care in the UK, you are cared for, and maybe a few months later, the hospital tends to run audits to make sure that the care that you were providing to patients in general was of the right type, was correctly provided, and achieved the outcomes and the goals that he had to achieve. And this is normally done post factum. It's done after you've been cared for. But AI can also help here. It can be used as a live auditing system that sits in the background, making sure that the care that is being provided is the correct one. So it's not being used to actively care for patients, but is being used to make sure that a patient is not misdiagnosed, that a patient is receiving the right amount of treatment and the right type of treatment. And if for some reason the performance or the outcomes of a certain department or a certain clinical service are not being good enough, then you can use AI algorithms to warn clinicians and warn hospital managers that something is wrong with the service that is being provided there. You also can use AI models to improve the way we manage our hospitals. So our hospitals are incredibly expensive things. They are very wasteful. And the reason that they're very wasteful is not because money is not well used. It is. Actually, the money is very well used in the NHS. Is the fact that things are very hard to predict in an hospital setting. For example, you need to know how many beds you're going to have available tomorrow, because you might have a bunch of patients coming in that require care in, I don't know, cardiology service, for example. And you need to make sure that a bed is available for that patient. But the problem is you do not know what other patients are going to come in. You do not know if other hospitals are going to transfer patients in. You do not know who's going to be discharged. And it's very hard to even figure out something as simple as, will I have a bed available tomorrow for my patients? And AI algorithms can be used to make those small measurements and those predictions that then allow us to manage hospitals better. For example, if I know that I'm going to have more patients tomorrow than I have today, algorithms can predict the amount of patients that you might have in your hospital, because they know what the patients are going to come in with, or patients are going to be transferred from other services. Enough nurses and doctors available to care for those patients, so that the service that is provided is at the level that it should be. But at the same time, that we never have too many doctors in certain services without patients to fill up their workloads. So it's really trying to optimize the way we manage hospitals. And when we put all of these things together, I think what's interesting is we start going on this journey, which is called the target is called the value-based healthcare approach to healthcare, where the idea is that we look at the full patient pathway. We look at the outcomes that matter to patients. So not only diagnosing and prognosing and correctly treating someone, but also ensure that the ultimate goal is what matters to patients, that they're being cared for in a specific way, and that their outcomes is something that they care for and that benefits them in some way. So is how do we maximize these outcomes while at the same time minimizing costs? Because we are in a socialized healthcare system, and we need to make sure that when we're providing care to patients, that we can provide the best care to everyone. So we need to split the cake in small parts, so the least amount of money we spend, the more care we can provide to other patients. And when we start looking at the patient journey as a whole, from admission to discharge, maybe a few months down the line, the idea of value-based healthcare really becomes very important, because you need to think about, you need to optimize outcomes while minimizing costs, and you can do that by looking at the full journey. So you might decide to do more analysis, more introspection, more assessments at the beginning, because that might save you money in the long term and it might improve outcomes. So rather than thinking about each event, each clinical service you're going through, and not optimizing everything as a whole, you can optimize the full journey at once. And if you do that, you can really massively reduce the cost of healthcare while at the same time significantly improving the outcomes. So in order to do this, we have been creating this AI center called the London AI Center for Value-Based Healthcare, for which I'm the CTO. So I lead all the technical development of all the platforms, software, and hardware. And the AI Center is actually now a consortium of 4 universities. So King's is leading the AI Center, but UCL, Imperial, and Queen Mary's are co-leading at the academic level. But then there's also 10 trusts, NHS trusts, which cover roughly 1/4 of the UK population. So those will be the largest London-centric research hospitals: Guy's and Thomas, King's College Hospital, Imperial Health, Barts, UCLH, etc. But also a couple of trusts in the south and southeast of England, so for example, Brighton and East Kent. And they cover a very large population. The idea here is that we develop platforms that can transform the data as it currently sits in the hospital, learn from that data and extract knowledge from that data. And then whatever it learns from that data can be deployed and used to care for patients. So there's this complicated process that we're going through, which takes us from raw clinical data as it currently sits in an hospital to something that can help save lives. Someone that unmuted themselves. So we really start from the patient healthcare record. So this is the different databases and computers and IT systems that the hospital would have that is going to store information about the patient, about who you are. There is a piece of software that transforms that data, which is stored in a way that is very specific to how that hospital works, and maps it to a common standard. So another database that is common across all the hospitals and that is harmonized, so that we know what the data is, where it's stored, how is it stored, and how to fetch different pieces of information that we might be missing. So the first step is really this harmonization step. And this is really easier said than done. This is a very complicated process, and it's something that is taking years for us to achieve. But the ultimate goal is that all the hospitals in the UK would then have a version of their own data that has the same characteristics and is stored in the same way, so that we know how to access that data and how to use that data to then inform downstream actions. The other thing that I think is quite important is that in countries like the UK and actually many other countries throughout the world, a lot of information about how you care for a patient is stored in the form of reports. So when you go to the doctor, they write some letters and discharge letters and letters for pharmacy and etc. And it contains a description of your symptoms and what you had and what you didn't have. So we need algorithms that can understand what text says and extract knowledge from that text so that we can action that text. And if we have harmonized data and information from texting certain care decisions, for example, why did the patient take a specific drug? Why was that drug recommended and not another drug? Did that drug that was recommended, did it actually work? Or did the patient come back a few years later with another pathology that is related, or maybe can yet come back to change to a new drug? And by looking at all of these complicated patterns, we can figure out for each patient what would have been the best treatment that we could have got to the patient to maximize the likelihood of the patient recovering and the patient surviving the disease. But also, we can figure out the things that we currently do clinically that don't actually work, that are not having a positive effect, because we can look at all of this historical data and understand all of these different patterns. We can do the same thing at the hospital level. So for example, we can predict, or we can figure out when did patient A move from a department to another department, for example, inside of an hospital. And by looking at these patterns and how these patterns change for every day of the week, from Monday to Friday and Saturday and Sunday, different months of the year, during the winter, during the summer, the patterns will change significantly because obviously certain diseases happen more prevalently certain times of the year. And obviously different days of the week and different times of the year interact with each other to know how many patients are likely to visit your hospital. And if you put all of this information together, you can actually understand very well where your patients are at the moment, where your patients will be tomorrow or maybe in a week's time, and who is likely going to be discharged and go home because they're cured, or who's going to stay around and is going to still be in your hospital maybe a couple of weeks down the line. And by being able to predict these patterns, you can then provision care and services to the degree that is necessary. If you now have all of this information, you can start finding patterns that you didn't know before. You can start training AI algorithms to exploit these patterns to make predictions that you couldn't do otherwise. For example, it might be that an algorithm figures out that a combination of certain blood markers and maybe some information from medical images together can inform the fact that the patient is going to develop a specific subtype of a certain disease. But you can do that at scale because all the data is standardized. So you can just push multiple algorithms to train in a computer and to explore data to understand which patterns work and which patterns don't work. You can do this in one single hospital, or you can do this in multiple hospitals at the same time. So you can connect the different hospitals around and train algorithms across hospitals without having to share data, because obviously clinical data is private. We don't want to be sharing it. So we can train algorithms in a way that the data itself doesn't move around, but the algorithms themselves are being moved from one hospital to another. And if you can do with enough a capture of different ethnicities, different age ranges, different genders, and etc., that will actually cover all the different presentations to make sure that the algorithms that we develop are general, are accurate, are safe, but are also fair from the point of view of equity and equality. When these algorithms are developed, and if we test them and they work, and we demonstrate that they do have clinical value, we can then translate these models to clinical use, because we can basically say we're now going to start using these models while the patient is being cared for. And when those things are deployed, it means that every time a new piece of data arrives into the system, predictions are being made, and those predictions or those measurements are being given to clinicians for clinicians to then make decisions that can help inform patients' lives and save patients' lives. So this is a complicated journey. But what I think is quite astonishing is it's how immature most of these systems are, not only in the UK, but pretty much elsewhere in the world. We're still stuck in the 1990s of informatics with slow computers and things like this. So creating this infrastructure is quite life-changing to the NHS, and it's something that is happening at the moment. So with this in mind, I'm just going to give you a quick demonstration of what that might look like. So this demonstration here that you're seeing is a specific application of this problem in the area of dementia. So this is part of my research. So here we are training algorithms to look at these brain MRIs, these brain scans of old people. And these brain scans are then processed. We can then train algorithms to be able to localize the different parts of the brain. In this case, these little bits of the cortex and the white matter and the gray matter. And we know that for example, when you have dementia, specific parts of the brain shrink, so they atrophy. And we can measure their size and compare it to the population expected distribution. So you would say, this is the size that I'm expecting the hippocampus to be for a 65-year-old female from this specific ethnic background, for example. And you can then compare to these normative curves for healthy subjects. And you say, oh, this part of the brain specifically is much smaller than I would expect. So if I was to show you, for example, images like this, where you see a fly-through of certain brains, the one on, I'm just going to move a little bit, the one on the left is a brain of a healthy person. And you can kind of see that by, for example, looking at this specific part of the brain. You see these black things that are showing now, roughly, are called the ventricles, and they tend to be relatively small in healthy people. But when you have dementia, your brain atrophies, so it fills up with fluid. So the ventricles grow, not because there's more fluid, but because the brain is smaller and something needs to fill it up. So the ventricular size gives it away. But when the patient has early Alzheimer's disease, the ventricles still look very normal, but there's other parts of the brain which will be affected. And it's very hard and very time-consuming for a clinician to be able to read these images. And the amount of expertise that exists in different countries, in different hospitals throughout the country, is very different. So we need to be able to create algorithms that can provide the same quality of care and improve the quality of care throughout the UK, regardless of the expertise that might exist locally in each one of the sites. So if I now take those images and I pass them through these algorithms, you create little reports like these. And these reports tell you how big these parts of the brain are in comparison to healthy matched populations. And if they're too small, they show up, for example, here as red. And you can clearly see that those areas there are very small compared to what they should be. But for example, in this early Alzheimer's disease patient, there's a couple of areas which are already small. And if you know anything about Alzheimer's, those areas specifically are the hippocampal and perihippocampal area, which are areas that are known to be affected first by dementia. So by having this information, anyone with minimal insights about the disease would be able to immediately see that this patient is likely going to be developing dementia, and already likely has an early form of dementia, which means you can then start symptomatic treatments much sooner. And actually, there's been a drug that has been released very recently and approved by the FDA, which might slow down, or which slows down the progress of dementia in a subset of the population. So you can see that these series of tools are taking complex information like an image or a piece of data, and is extracting knowledge that we understand, and is summarizing that knowledge and presenting it to a clinician in a way that they still own the diagnostics, right? They are still the ones that are finally and ultimately diagnosing the patient, but they are using much more informed decisions, and they can have data that supports their decision rather than just having someone looking at an image and saying, yeah, that bit there looks a bit small, and thus I'm going to say this patient has Alzheimer's. So we're trying to move from intuition-based care, where you're relying on clinical expertise, into evidence-based medicine, where the evidence here is given to you via algorithms that can help you extract that evidence in situations where it might be too time-consuming to do otherwise. So just to move on a little bit further, these algorithms here, they require a lot of compute capability. So we've been these days talking about the processes and the kind of information that they can extract, and we've seen what these algorithms can do, and the kinds of things we can extract from these images. But the problem is, when you start scaling this up, when you start training bigger and better algorithms, the requirements for compute capabilities start growing immensely. So these algorithms already use GPUs, so these graphical processing units. They're the cards that you normally use to play games in your computer, but we use bigger versions of those to train these models. And we use these very big computers that have tens of these cards, if not hundreds in certain situations, to be able to train these algorithms. So you actually require a much bigger scale, in the same way that the biology lab will require very good microscopes that cost millions of pounds. The same requirements are now happening in the healthcare data domain, where we need to have the investment to build infrastructure that allows us to train the algorithms to the degree of accuracy that is needed for healthcare. And you can imagine, if you're training an algorithm to detect between a cat and a dog, if the algorithm fails a couple of times, not much happens. So the performance is less critical. But in healthcare, if your algorithm does not perform as good as it can perform, you are literally harming someone. So it's an ethical conundrum where you want to apply these algorithms, but you need to make sure they are as good as they can be and safe as they can be, to make sure that, and to do so, you need to have the computational infrastructure to deliver this. So jointly with NVIDIA and a bunch of other partners in the UK, there is now this new supercomputer, which has been made available online only a few months ago, called Cambridge-1. Because it's physically connected and linked to the ARM offices in Cambridge. But Cambridge-1 is basically a new supercomputer that has been installed in the UK by NVIDIA as part of a recognition of the amount of healthcare research that is happening in the UK, and as kind of a donation to the country, for the country to be able to benefit and to run bigger scale research that is able to actually utilize these GPUs at scale. So Cambridge-1 has partnered with a couple of very large pharmaceutical companies like AstraZeneca and GSK, but also with King's College London and with Guy's and St Thomas NHS Trust. So is the only academic and clinical partners of the program. Everyone else is an industry partner. And these partners basically are currently utilizing Cambridge-1 to do much bigger research and to run algorithms at the scale that you wouldn't be able to run otherwise. So as a proof of concept use of Cambridge-1, so we were lucky enough, we at King's College London were lucky enough to have access to Cambridge-1 prior to Cambridge-1 being released. So we were given the keys to the big machine a few months before. And we basically started thinking about what would be a cool project that we could run that will actually make use of that scale. And what we came up with was the idea of data privacy and the lack of information and lack of data that exists in healthcare. So when you're doing healthcare research, one of the main limiting factors is it's hard to access patient data, and rightly so, because patient data is private and we need to have consent and ethics, and we need to have the appropriate governance and etc. So it's very hard to have access to enough data often to be able to train these algorithms. Sometimes we need millions of examples to be able to train something accurately. So rather than being able to just ask for access to millions and millions and millions of data sets, we decided to train algorithms to be able to generate what is called synthetic data. So data that has the same characteristics as real data, but is computer generated. And then we can use this synthetic data to then train other algorithms to recognize the patterns we need from synthetic data rather than from real data, which means you can bypass a lot of the problems of governance and privacy and etc. And this idea of synthetic data has been around for quite a while. So for example, here on the screen, you have different synthetic data projects that have happened in many other areas. For example, those landscapes that you see on the left, they've been generated by algorithms. They're not real places that exist. These two humans that you see just behind me, they are, again, they do not exist. They are completely synthetically generated. And these are algorithms that have learned from images of faces or images of landscapes. And you can then ask the model, can you give me a new face and a new face and a new face? And you can generate an infinite amount of them. But what's really interesting is not only you can generate an infinite amount of data, you can be very prescriptive about what you want the data to contain. So for example, you can say, I want to have a male 54-year-old white Caucasian heterosexual person. I'm just making things up at the moment. So you can be very prescriptive in what you want the data to contain. You can say, I want a person with a goatee. I want a person with some sunglasses, for example. And that's because when you're training the algorithm, if you know the characteristics of the data, you can say, you can show the data to the algorithm and say, look, this is what a face looks like when the face has glasses. And the algorithm understands the concept of glasses without you having to tell the algorithm what glasses are. You just say, this face has glasses, this one does not. And the algorithm understands that the difference between them in the same way that you and I would understand. So we can apply the same concept to medical data, where you can, for example, say, I want to generate images of this patient with these characteristics, with this specific pathology. And by doing so, you can then generate a very large amount of information. The problem is to do so, all of these examples that you're seeing here on the screen are two-dimensional images. So they're images of their pictures, they're 2D images. When you're taking a picture of someone's brain, for example, you need to scan the full three-dimensional head. So your image, rather than becoming just one picture, like you take a picture of someone's face, it becomes a series of pictures as if you were slicing through the brain. And that means the size of the computational infrastructure that you need to be able to train those models is much, much bigger than what you would require to train images like the ones you see here on the screen. So through this algorithm, we spent a few months developing it. Actually, we had a lot of the foundations. We just had to scale it up to make use of the Cambridge-1 infrastructure. And we were able to do like a little PR. I mean, the paper is currently being submitted and in the process of being reviewed. But we were able to scale it up to the full Cambridge-1 to be able to train this algorithm in a way that we can generate synthetic data. So for example, this image that you're seeing here is an image of a human brain, brain MRI T1 image more specifically. And this T1 image of this brain MRI is of a human that does not exist. So this is the brain of a person that does not exist. It's a new brain that just doesn't exist on Earth. You can see a few things from this data. So you see that the data has been blurred. So the data that the algorithm has learned from has been blurred around the face and the ears, because that's to avoid, and that's for privacy reasons, to avoid, for example, using three-dimensional reconstructions of brain of faces to be able to re-identify who the person is. So the data that it starts from is fully anonymized, and there's no way you can recognize patients from that data. But the algorithm has then learned the patterns on that data, And if you can now throw away all the original data that the algorithms have learned from, and just ask your new model that you've trained, can you now give me a new brain? And this is the image that the model comes up with. We're currently still doing some testing and scaling it up a little bit further, but it's producing images of quality that can trick radiologists. And these are clinicians that are used to looking at imaging data on a daily basis, and they can trick clinicians in many situations to think that these are actual real brains from real people, even though they are fully synthetically generated by a computer. And so the idea is that we're using this, and when these models are trained, and when they're trained to the degree that they need to, and with a degree of fidelity that they can be trained, we should be able to use these models to generate data to be able to train our algorithms without the need to go back to patient data, unless there's information that is missing, and then we can just train the model a little bit further on the missing information. The idea is that we can bypass this need for privacy information. So this hopefully gave you a bit of an insight towards this journey where we went from raw data in an hospital to being able to transform the data into a format that we can use, learn from the data, and then deploy algorithms that can act on the data. You've seen a couple of examples, in this case, at least one example using Alzheimer's disease as a demonstration of what these algorithms can look like in reality. And the AI bit is just a small bit in the middle. And obviously, there's a huge amount to build, a huge amount of software and platforms that are being built for this to become a reality. But the magic happens in that small bit, that small AI algorithm that exists in the middle. And then when you take these algorithms through this process, you can start creating more and more complicated questions and more complicated solutions to these problems that allows us to scale and ask questions that we couldn't ask otherwise. And hopefully at the end, you've seen that in infrastructure like Cambridge-1, which initially we used to run these proof of concept projects. I'm not entirely sure if you're still seeing the video now or not, given some comments that I've seen there in the chat. I just played the video again. But what I'm trying to get to is that Cambridge-1 really is an enabler of very interesting questions that we couldn't answer otherwise. So while this video that I'm showing here, it was a proof of concept project of generating images, but the ultimate idea is that we will be in a position where we can take all of this information and we can use Cambridge-1 to train more complex algorithms and algorithms that can make predictions of things we never imagined before and hopefully help save someone's life. So I'm going to stop presenting now, and I can already see from the chat that my connection has not been the most excellent, but hopefully you managed to get most of what I was trying to get through. Tom, how bad was my connection?
If it had been very bad from my end, I would have jumped in and warned you. But every time, for me at least, you kind of came back in. So thank you so much for that, George. Certainly, I think I knew where you were going on that direction. But if there might be some people who missed little bits who have questions, which is exactly the opportunity that we now have the rest of this session for. And as I just mentioned in the chat, if someone was missing, let's say the synthetic brain video, we can run it again, or maybe we can run it with real brain footage and see if someone can spot the difference. So thank you so much for that. This is the opportunity for people to ask any questions you might have for George. Apologies if there were a couple of moments when we were losing connection there. Inevitably, with the current situation as normal, we are sort of all working from different conditions of internet connectivity and so on and so forth. We don't all have a NVIDIA supercomputer in our offices, unfortunately. So please feel free to put questions into the chat. But in the meantime, George, I promised you I was going to ask you some questions because I have loads. So I'm a public engagement type person, so some of my questions might come from that kind of angle. And one of the things that I really wanted to sort of dig into to start with, supercomputer is such a big word, and we've bandied it around, but we've been bandying around the word supercomputer for as long as there have been computers, which is a decades and decades long history now. So when we talk supercomputer today, what are we really talking about in terms of processing power? I mean, that looked like we're back to room-sized computers. Tell me about this toy you have access to.
Yeah, I mean, the scale of compute nowadays is a bit obscene compared to what you had in the past. So, for example, one of these, you see in each one of these little racks that you see, one of these white blocks, there's two of these golden They're called DGX A100s. They're a single unit, and we're plugging or NVIDIA has plugged 80 of these. A single unit like this is probably more powerful than the fastest supercomputer we had maybe 10 years ago. And this is like the ones that would fill in almost a computer stadium size room. A single one of these boxes is probably more fast now than it was 10 years ago for a full room supercomputer. So you can now imagine what it means to have 80 of these connected to each other, all of them with incredibly fast connectivity and things like this. So we are in the teraflops. So this supercomputer specifically, Cambridge-1, is actually currently in the top 30 most powerful supercomputers in the world, but is actually the most powerful supercomputer in the world specifically designed for healthcare applications. So there's some design decisions that you need to make when building the supercomputer, depending on what you want to use it for. And this one has been particularly designed for the kinds of workloads that exist in healthcare. So it's actually the fastest supercomputer in the world, specifically designed for healthcare purposes.
So I can see some questions coming in, but I did want to have a quick follow-up. You mentioned the the specific decisions that are made. Could you give us a little bit more detail on what that side of things is?
So, for example, when you talk to people in doing research, for example, also using supercomputers, but in computer vision, so distinguishing between cat pictures and dog pictures and YouTube videos and things like this, which happens all the time. 2D images are relatively small. They maybe are a few kilobytes, maybe a few megabytes on your computer. A brain image could be hundreds of megabytes, if not gigabytes. A digital pathology image could be terabytes of information for a single image, right? This is filling in completely your computer hard drive and more with a single image of a slice of, for example, a prostate tumor.
Yeah.
The amount of data and the size of each single element of data is huge. So while in many other areas you tend to have billions of records and each record is very small, in healthcare you tend to have thousands and maybe hundreds of thousands and maybe a couple of millions of records, but each record is very big. So the amount of data that is being transferred and the datum, the quantity of each one of these pieces of information needs to be taken into account on how the connectivity is established between all of these different nodes. So it's just a slightly different workload, but it changes significantly how you design and how you provision these things.
Fantastic, thank you. This leads very nicely into our question that's just come into the chat from Andrea here. So with all of that in mind, what are the main challenges, external and internal, in implementing AI into the NHS? It's hugely powerful. My understanding is that not every NHS system is quite up to scratch technologically.
But it's not, and the technology that NHS is building on is obviously quite dated. So as part of our AI center, one of the things we are doing, and this will sound weird, is we're literally, so one of these vertical racks that you see here, we are installing roughly the same as you see in one of these vertical racks in each one of the 10 trusts that we're working with. In this single room, we have 80 of these, but we're putting one of these inside each one of these trusts. For you to train the AI algorithms, you need a lot of them. But for you to use the AI algorithms, you can actually get by with a lot less. So we're physically installing the hardware of the type that the NHS never had in their inside of their infrastructure, and being able to convince people that this is something that they actually need to install to make sure that the systems can support these, that people know how to maintain them and how to manage them. And those are small intricacies that sound quite complicated, but this is just the first step, because if we don't even have the hardware to be able to run these algorithms, there's nothing else we can do. But there's much more, right? So the hardware is dated and we need to improve the hardware, and we're using the AI Center as a way to demonstrate that this hardware, if installed and made use of, can have much more value, significantly more value than what it costs to provision and to purchase. But there is also a cultural shift that needs to happen. So the NHS is relatively slow moving, and in the AI world, things tend to move relatively quickly. And obviously there's a clash between how fast things move and how fast can they move to make sure that they're still safe for patients. So the NHS needs to be made much more flexible and faster at approving things. But at the same time, AI development and AI research needs to be made slower to make sure that when you do something properly and is made properly safe and properly tested. And there's I wouldn't say a clash, but there's a synergy that is happening at the moment where NHS is learning a lot from AI researchers and vice versa, and hopefully they're meeting each other in the middle, where we can have a good balance between safety and speed of development, so that we can maximize the impact that we have. There's also a lot of other smaller issues related to, for example, ethics and privacy, because obviously we're playing with, or we're working with patient data, and depending on what you want to use the data for. If you just want to do research, pure research, you need to have full ethics, which requires patient approval and etc. If what you want to do is what is called service optimization, so to improve the quality of service of a patient, then that falls under standard use of data. So, for example, hospitals currently use patient data to be able to know how to improve the way that they care for patients. It's a fair use of the data. So there are certain situations where you can make use of the data for specific purposes without necessarily asking for individual patient ethics, by going through national boards that can approve some of these things. So there's a lot of steps on how do you do this, which again slows down the progress. And there's a culture shift that is happening now in the NHS, with agencies like NHS Digital and NHSX trying to push for that shift to happen, so that AI can actually have an impact in the next 10 years rather than in the next 50 or 100 years.
Fantastic. We've kind of touched onto ethics there, and I think that's kind of part of the answer, perhaps, to this next question, which has come in, which is if brain scans could be made anonymous by blurring the facial features and so forth, why do we need to generate synthetic data? I mean, I want to ask you a lot of questions about synthetic data. But let's start with that difference. Yeah.
There's two questions. There's two things there. First of all,
can you say that last bit for me again? We lost you.
Wants to say, how can you make an image anonymous? Sorry, can you hear me now?
That's better again. Yeah. Yep, you're good, I think.
So I would just, a definition of anonymous is a tricky definition. So one thing is, how can I make that image anonymous, that if I manage to get the image, and if I do something with that image, for example, I do a 3D rendering, you can not recognize who that person is. From that point of view, blurring someone's face is making the image anonymous, because there's no other way you can know who someone is apart from the facial features. But the technical definition of anonymized data, the way your brain folds and the way it twists around is like a fingerprint. So it's very specific to your brain. So there are still some reasons why some people would not consider that data to be fully anonymous. But because all the training is happening in a trusted research environment where there is no access to data, and I don't have access to the data myself as a researcher, the algorithm does, but I don't, there's a separation, and the data is still deemed to be private. But actually the need for generative data, or for these generative models, is much more than that. It's the fact that we can control what the algorithm does. For example, it might be that we don't have a lot of information about what a 64-year-old female from Afro-Caribbean background with dementia looks like from the data set that I have, just because I don't have many patients that come from that background in some of our hospitals. In those situations, you might want to ask your model to generate specific subtypes of the population that might be missing, so that the algorithm can be made robust to shifts that might exist in terms of the phenotype and the appearance of certain pathologies. So controlling the data that can be generated, and an algorithm understanding what that data looks like and what happens to the data when you shift, when you move these knobs around, these age knobs and etc. is a very important characteristic for us to ensure that the algorithms are actually safe and fair from all points of view that are required by law. So it's complicated, and there's a lot of small technical issues as to why we're trying to do that.
I think the answer to all of the questions is going to be it's complicated. Although I really appreciate you like trying to take a through line for it all. So a couple of more questions up. In terms of the AI training, is this focusing predominantly on specific data, e.g., Western diseases such as diabetes, heart disease, or on the so-called common or neglected diseases, for example, tuberculosis or cholera? So kind of, I suppose the question is really, where are we training our AIs primarily at the moment?
So the people training the AI models, they tend to train the AI models on diseases that affect the population in the places where these people live. Obviously, there are funders that fund specific model development and research in deprived areas and deprived diseases, and those ones will be focusing on things like tuberculosis and cholera, right? So I have many colleagues that work in low-income countries and that actually have physically moved there temporarily to be able to help develop algorithms specifically for those purposes. But unfortunately, the data we have access to is data of diseases that commonly occur in the UK. And because of that, we tend to focus on diseases that exist in the UK. Through the use of technologies like federated learning, and if the platforms we are developing for the NHS are then adopted internationally in other countries, or at least compatible platforms are adopted elsewhere, there is a way for us to train algorithms across multiple countries without having to move data. So you can actually start having the skill that is necessary to tackle some really rare diseases. But it's not an easy question, right? There are diseases that will be really rare for many years, where not only the knowledge about those diseases is rare, but we don't have enough data to be able to train algorithms with sufficiently good quality. So it's going to be an international cooperation to make sure we can achieve the scale so that the algorithms can make sense of the scarce information that might exist in certain rare or maybe neglected diseases.
Okay, thanks. So we're just there's a question here about research ethics committees in the UK, but then we've just touched on international cooperation as well, which adds a whole extra tier. But so the question is, how are the research ethics committees in the UK prepared for this shift of including AI in the NHS, and that requires patient data and the population at large? So I mean, really, we're sort of how ready are we for the questions that this technology is already opening up for us, and what work needs to be done?
So I guess there's two answers there. So one of them is on the how ready they are. So there's a lot of principles when you apply for ethics that often don't apply to AI models. For example, the principle of data minimization is probably one of the founding pillars of ethics. You only use as much data as you need to be able to answer the question you have, which makes sense if you're doing exploratory evidence-based research. But we know that, for example, for AI algorithms, the more data you have, the better the performance is going to be. That's just a fact. So, for example, minimizing the amount of data means that you are limiting the performance by restricting yourself to a subset of the data. So it's counterproductive to try to minimize data, but that's actually a requirement in many ethics committees. So there are small things like this where certain the technical requirements of AI models, both from the point of view of the type of data, the variety of data, the breadth of data, the fact that the algorithms can find patterns on things that we don't necessarily know in advance, are things that ethics committees are not normally very keen on, because they like very well-defined questions where you kind of understand the relationship in advance. So there's a transition that is happening there, and they are becoming much more open to broader questions where we say, we don't necessarily know what the pattern should be. That's why we need all of these data to be able to figure out which part of these data is predictive of whatever outcome we want to predict in the end, for example. But that, again, links up with, as you were saying, it links up with all of these questions of international collaborations and etc. And when you're doing research at scale, and when you're doing research across multiple trusts and actually across multiple countries, it becomes complicated to make sure how do you make sure that the ethics are compatible and that governance is done properly and etc. So we decided to do something that is called federated learning, and that's something that I was describing already, which is this idea of you can train algorithms across multiple hospitals at the same time without having to exchange information. So the algorithms travel between hospitals, but the data itself stays there. And the good thing about federated learning is that that can also scale internationally to multiple countries with completely different governance and ethics infrastructures. So as long as different hospitals in different parts of the world are keen to participate in that bigger research, the idea of where the data is stops becoming an issue, because the data is always going to stay in the place that the data is collected. And it becomes now a question of how do we make this algorithm communication and transportation secure in a networking sense. So it's a process that is slowly evolving, but there is a technical solution to the legal problem of ethics and governance and privacy, which is still evolving and will probably continue evolving for many years to come.
I'm sure it will. I mean, that's kind of a question that's talking about the ethics committees and within sort of the internal infrastructure that we're all working within. But I kind of wanted to expand on that question, if you don't mind, and talk a little bit about public understanding of those questions, which is always, a huge influence in policy and direction of research funding and so forth. So we've never been in a situation where the spotlight hasn't been more on healthcare thanks to the COVID-19 pandemic, but at the same time, kind of public understanding of both the problems and the technological solutions that are being developed is perhaps not where it should be. Are there any particular things that you as a technologist would see as being a challenge to that public understanding and that public communication? And indeed, can you offer any of us in that sort of space some ideas that we might be able to actively pursue?
Yeah, so I think probably the hardest question to communicate, and again, we've seen that with COVID, is the population's perception of risk and risk and outcome. Right. So how do we, for example, why do we make certain decisions on who should get the vaccine and who shouldn't at the population level? Who should be prioritized and who shouldn't? And there's a complex set of equations that you need to do to try to figure out like who will actually benefit from this and who wouldn't and who should be prioritized and etc. And it's very hard to communicate that to the population because people don't necessarily understand marginal risk increases by doing one thing versus doing another. Like how much would the vaccine help versus something else, right? Or versus like getting infected first and then getting the vaccine afterwards or something like this.
Yeah.
It's very hard to communicate that. And it's the same thing with AI when applied to anything. For example, if you say, I'm going to apply AI to a self-driving car, what is the risk of doing that? If a self-driving car kills one person for every million miles drive, is that a bad or a good thing? Most people in the population will see that single death over millions of miles driven as a very negative thing, when in reality, that's much, much, much better than what actual humans do when it comes to them driving, right? But humans don't like to compare themselves to themselves because they know that they're bad, right? Same thing happens in healthcare. Healthcare provision in the UK, and the UK is one of the best places in the world that you can be treated for something, is not very good in many areas, right? You are often not well diagnosed and you often don't receive the best treatment. And that causes a lot of harm and death and etc. And obviously many things can be improved. But we just accept that because we accept human error, because we think humans as humans. But when it comes to the use of technology like data analytics and AI, people tend to see the use of computer as not being able to fail because they think about AI as a deterministic process. And if there is a process that you can go through, the process should always be the same and should always be correct. But it's not that simple. Is the system is uncertain. And when we deploy any kind of technology that does not have a deterministic outcome because the system is not fully understood, we need to be able to communicate what the risk is. We need to be able to accept that there is a risk. And we need to look at statistics at scale to make sure that it is beneficial to patients, that the technology is used and is indeed helping save lives. So I think how do we communicate risk versus value of this technology that is misunderstood is something that I think is very important and is really lacking anywhere in the world. I don't think there's any country that is very much advanced in this domain.
Okay, fantastic. Thank you. I was just going to post something into the chat there, but it's not working. So instead, I'm going to invite people to come in for any last questions. We've got about 5 minutes left on our schedule here. If anyone would like to put in a final question. Oh, we're just getting the praise bit now. Very good talk. Thank you. So we can just sit back and take rounds of applause virtually if you prefer, George. But maybe.
And that's in advice for any networking issues. I understand that my connection today has not been very good, but not much that I can do, unfortunately.
I mean, I think if anyone has any follow-up questions, obviously you're part of King's, you're very findable. Perhaps if you're happy to put a contact in the chat or something, that'd be fantastic for anyone who has the very specific questions. But as we're sort of wrapping up, then I suppose if I had one final question for you, if I may, it's to kind of look at the idea of cost. We're obviously talking about very large investments in technology provision, and the benefit for that is those efficiencies in healthcare, future healthcare that might come in. But a lot of people will be concerned when they hear efficiency in that sort of sense, especially here at a festival of disruptive thinking. When we talk disruptive thinking and entrepreneurship, it's often, we could be talking about just-in-time supply chains and AI and just like last-minute kind of things. And of course, there's a lot of issues around just-in-time supply at the moment in here in the real world. Is it is it those kind of efficiencies that we're looking to put into NHS type organizations, or is it more about those unseen patterns that you were talking about, finding efficiencies that a human wouldn't necessarily recognize, but an AI could be trained to find? I guess I'm looking for that cost to balance ratio.
Yeah, so the NHS has this saying, which is get it right the first time.
Right.
That's basically where the efficiency comes from, right? And get it right the first time might mean multiple things. Might mean doing more analysis and more a deeper assessment of the patient the first time around, so that we get the right diagnosis and you get the right treatment at the right time. So you're reducing the amount of time it takes to care for the patient. And by doing that, you actually end up saving a lot of money. But not only saving a lot of money, you end up having a much better outcome for the patient. But it might also be that by finding patterns that you've never seen before, you can now find the best drug that the patient should be taking the first time around, rather than spending 3 years trying to jump from drug to drug until you find the one that works for you, right? So it's a mixture of everything. Is how do we make sure that we're shortening the journey to the minimal essential number of steps that in the end give you the best outcome possible, by using the least amount of funding necessary, so that we can then improve the technology and the kinds of treatments that we would provide with whatever money is saved by doing all of this. And this is really easier said than done, because all of this requires a lot of change in hundreds and thousands of diseases. And all of them have particularities that interact, for example, with the kinds of doctors that you have in an hospital available that day. The fact that the hospital might have a certain machine means that is very hard to standardize. So we cannot just think about hospitals as this epitome of standardization. We need to think about clinicians as humans. We need to think about them caring for human beings as patients. And how do we make sure that technology can be used in that setup to improve the efficiency by making sure that we can find the right diagnosis the first time around.
Well, thank you very much. So I think as we come to the end, George, thank you so much for this fascinating hour. I feel 100% disrupted in my thinking. For those in the audience who'd like more, I have just posted a link into the rest of the festival. As I mentioned, this is the first of a series of events happening this week and next week. So hopefully I might see you again for another one of these. And before you go, I've also posted a link for the Entrepreneurship Institute's newsletter. If you want to find out more about the events that they're organizing, they promise many more things like this to come. And they also promise, apparently, the offer of a goodie bag for anyone signing up during the festival. I think there's a chance to win stuff. So, you know, what more can I say except goodie bag? Click the link. Everybody, thank you so much for your time. We'll hope to see you again. Enjoy the rest of your weeks. And I know we're all silent, so a round of applause from me for George. Thank you so much, George. We'll see you all soon. Thank you.